good morning. All right, we got a few awesome talks this morning. Jun from Fieldview? Oh, from Climate. Oh, yeah, that's right. You're from Climate, yeah. Talking about Agstack. Take it away.
Thank you. Can you hear me? Excellent. Morning, everyone. My name is Xiong. I'm a remote sensing scientist coming from Climate Corporation. It's a great pleasure to be here to meet you guys and to talk about some of our recent effort we're heading to. We call it Agstack. It's an open data cube standard for digital farming. Actually, I'm a little bit curious why I picked this title, because it seems too broad to elaborate. But I guess I will try to cover some very basic aspects of this topic, like why climate initialized Agstack, and how we define Agstack, and what is supposed to be work. So first of all, why climate initialized Agstack? So at the Climate, we are dedicated to develop technologies which can transfer the field data into the meaningful insight and help the farmers to sustainably increase the productivity and manage the risk. And as you can see from the slides, the data tells us the gaps between the corn yield winners and the average levels. There is opportunity over there. We're not saying we aim to fill the gaps, but we do want to narrow down the gaps. That requires us to focus on collect a lot of data and do the analytics. We try to, if we want to solving the yield estimation equation, we're always collecting the data seamlessly. We have the real-time data from the planter and the harvester. We call it combined data or machine data. We have ground measurement from the climate research farms and the Monsanto Agency research trails. We have the custom data from the field view apps, including the scouting photos or scouting notes. We also have data from other agricultural industrial software systems. So think about how to put all the data together and do some analytics and find the connection between them. Just imagine what the mess we have for only the raster imagery community. You can say the complexity we are facing is even more higher. So, for example, I just wonder anyone in the room has touched the raw data from the harvester. This is how it looks like. And I do hope none of you had issues with trypophobia, because this is exactly the first time I saw these maps. This is how I feel. So the complexity of this yield data is, so in one field, you will have thousands of these very slim strips of polygons. So each polygon comes with the measurement, the wet weight of the crop, which has been get from the mass sensors, and also the exactly shape where the harvester collected the crop. So if you want to, our modeler will do some local starting with this data. So we can use it like a vector format. But if you want to do some more scalable analytics, you have to find a way to align it with remote sensing pixels. And the complexity of the problem is, this polygon is much smaller than a single satellite pixels. I put a sentinel pixel over there. So it's usually smaller than that, and it could be also across different pixels in the next to each other. So if that happens, you have to do a lot of things. You have to cut it into subparts to the individual sentinel pixels, and you have to calculate because this is wet weight, so you have to calculate the values belong to individual pixels according to the proportion of the errors. And then after you finish all the processing of the polygons, you have to do the aggregation to get to the actual values of the individual pixel. So you may wonder, does that really matter? You really need this accurate yield data after so many tedious work? The answer is yes. If you do care about looking into the variability within the field, this is data. This is the way you have to play. And this is a very big data set. This is what we have from the 2018. So 2018, we already collected more than 10,000 compiles covering millions of actors. And this data is even increasing. So after the users install the Climate Drive apps to the harvester, it will connect the sensors and uploading the yield data to our servers. So we see a lot of, we have seen a lot of chart to show how the remote sensing data exploding, how it increased exponentially. But to us, this data value increasing happened in remote sensing data, happened in machine data, happened in custom data, at all the place. So how to make all this data easy to find, easy to query, searchable, discoverable, operable, and scalable to our modeling is the very first step to go. And this is a very brief summary of the requirement of data cube for agriculture. A very simple, straightforward definition is Agstack is an analyst-ready data cube for data-driven model at large scale on digital farming. Should be built on the top of STAC and ARD framework because we really want the data can be queried instantaneously and also processed systematically. And it should be across sensor fusions because for the agriculture application, we always have the inclination. We won't stick to one or two primary data sources. We want to use as much as data as we can if the uncertainty is understood. And we want the interoperability between combines and satellite and UAV data. And it should be able to multiple temporal spatial alignment because of different application scenario. For temporarily, we should have daily, weekly, monthly growing season. If you want to do phenology monitoring or yield estimation, you have different temporal scales. And spatial scale, we have subfield, field, regional scale. So, but what Agstack is? Agstack is standard because it's a very complex questions. In order to do that, a possible solution is we won't have a perfect one solution for all these questions. A perfect solution is widely agreement standard to further our understanding. And what Agstack is not a standalone product or pipeline or services. We may have some microservices like a STAC catalog, which provides the user some functionality to carry the data. But we realize this is a great commitment. This is not any organization can do at this moment. It requires the whole awareness of the whole community. And this is an example of the Agstack cube, according to our understanding. So it's an enhancement of the remote sensing data cube ARD product. So first we have raster ARD layers, which include the public and the platform partner data integration. Specifically, we want time series from the TOA, grayness, the vegetation index. We want to specify how we do the cloud mask, mosaic, and clip. And we also want the DM, soil, weather layers. So for the machine data, we have the planting and harvest data. We have the fungicide and the pesticide management. We need to specify how we do the quality control and cleaning, and do the restoration at the field level on demand. So for the custom data, which provide important information at the field level, so it will be also introduced in the future. So we need to know how to do the clustering and put it in like a label, so we can use machine model to drive them, machine learning model to drive them in the future. So this is right now something we are doing. In order to introduce the machine data into the Agstack, we working on a machine data stack extension to link the GeoJSON, the raw data from the machine data, and the restoration Beautif if needed. So through this way, we can handle the following pipeline transparently for the scientist. So once we have the combined data, combined polygons in our data well, so we can specify any ARD product ID and get the combined matrix immediately. And after we're doing that, we can combine this ARD product as well as the combined assets into the same data cube, and go to explore the relationship between the imagery time series and also the yield map. So this is a very conceptual, simplified architect of the Agstack. So we have the data component as well as the process component. So for the data component, we have catalog services which wrap all the data requests from different data sources from the different infrastructures. For example, we have the stack core, which can enable us to search the data set from our own raster platform. And we have this stack extension to handle the machine data. And we also establish mechanism between us and our partners to exchange the metadata. So we can transfer our image request to their platform and get the stack result back. So in this way, all the data query can be under the same umbrella, have the unified interface. So, and based on that, we can make our life easier to build the ARD profile. This is an example when we move this idea to a production level. Yes. Yeah. Yeah, thanks. Yes, once the user could be our internal scientist, could be one of our internal services, request the GeoJSON request, and it can go to the Stack's server to run the predefined pipelines and get the combined field asset on demand on the fly into the cache and combine with other data cube and return to our researchers. Another example is we will reflect our pipelines, existing pipelines, into ARD processors. So this is an example of the cloud mask. And this is the outline of this ARD processors proposal. So we will document this and describe is any open source license it has been used, any other data sets in order to build this algorithm we collected from the field, from the farm, and what's the dependency, what's the input data of this algorithm, and is any data sets available for the validation and evaluation. Another thing I put it here, but in the end, but not, is also important is the distributed training scheme. So we have lots of data, and it is a block when we try to build this, to train this model. So we test our training model on different distributed platforms like AWS, SageMakers. And the point I made here is the challenge is not only come from the data preparation, it also comes from the computing when we move to the big machine learning modeling. So you can see from here is this is not a pure parallel process, because after we collect the data cube, we crank in tilings, we have to do a big loop to do the preparation. And then we can do the distributed trainings. So this process is not 100% parallelized right now, for now. And that will be the bottleneck for the next step. And here is a tentative timeline for this Agstack. So you can see we started very recently, and right now we're looking into the stack part to establish the full metadata for our imagery and the machine data. And in this year, we will focus on the documentation and establish the minimal prototype and use case. So again, I want to say this is should be community aware. We want to make it aware for the whole community, and it's great to align all the effort and all the considerations for the whole community for the same purpose. So please let me know if you have any feedback and comments, consideration about this topic. And that's what I have. And I'm more than happy to take questions, if any. Thanks.
Thank you, Jim. Yeah, we got time for a few questions. Mike.
Yeah, if one of the slides.
You want to use the microphone?
Oh, sorry. I feel like I'm projecting my voice pretty well.
You're doing pretty good.
Yeah. This mic's kind of scared me. I don't know.
Testing. One of your slides showed that this was specifically for rapid eye imagery, and I was just curious, was the plan to extend it to other data sources? Was this just like a prototype proposal, or I just
yeah, so when you see the processes, it will be a library. So the library will be grouped in different catalog, and every catalog has many proposals. So every proposals will, we try to slice the proposal into as small as one to represent the either specific. So for example, for the mask, we will have rapid eye, have Sentinel-2, have Planet. We build the library first to get the standard, to make people understand what kind of information you need for this standard. Yeah. And then we do the recommendation. When you want to build the pipeline, this is the roadmap you need to go.
Do we have any other questions? No? Okay, all right. Well, we'll move ahead since we're already behind. So thank you again, Jen.
Is it okay? I guess that should work. Okay. Okay, let's try this setting. Is this the resolution it should have? I don't know.
Do you want to mirror it maybe?
Yeah, I'll try. Yeah, well, okay, could work.
This usually fits the resolution for the
Okay,
display there.
okay, good. Okay. Yeah, now we're set. Hi everybody, my name is Joachim. I work for EOX. We are a small company from Vienna, Austria. We are mainly affiliated with ESA. And today I am going to talk about one of our newer products. It's called EOxCloudless. And generating cloudless mosaics out of Sentinel-2 data and putting this into context of the topics of this workshop, namely ARD and STAC. So I will share some insight how we do our mosaics and what issues we faced and how we could influence and use STAC standard and ARD. So we have this web page since 2016. So in 2016, we did our first global mosaic from Sentinel-2 images. It went pretty well. So so 2 years later, we did a reprocessing using more recent data. You can go to this web page. We have an open WMTS endpoint, so you can use it for free as long as you use the proper attribution. And yeah, we'll be happy to see this map being used as far as possible. So once we did our first run, we improved our algorithms and extended the capabilities. So then we came up with this idea that cloudless mosaics are not just, because our first intuition was to simply create a visual product. So like what you know from Google Earth. So to use as a base map for mapping applications. But then we figured, yeah, we could also include multiple bands, so like the near infrared band or whatever is required. And this is encapsulated under the term or under the product name EOxCloudless. So what you see in the bottom right corner is actually a Sentinel-1 mosaic. So we are doing it with radar data as well. And on Cloudless EOX AT, you can get some more information on these products and the different flavors of mosaic we offer. So there's a main distinction. So we have on the one hand, we have our viewing product. So the mosaicing algorithms there are optimized for viewing purposes, which means we aim to make it as seamless as possible, but of course at the cost of the original values. But you don't need the original values if you want to show it. And then we have the data products where we aim on maintaining the true pixel values as far as possible. So we have various mosaicing algorithms which reflect the different requirements we get. Yeah, but the core system is always the same. So we are reading the time stack and then collapsing the cube into one layer by certain rules. What we also do is sort of some algorithms that keep the original pixel values. We can actually add an index band to the output TIFF, and via a GeoTIFF tag. So we append a JSON which acts as a lookup table. So you actually can map every single pixel to the original data take it was being taken from. So this, and what you see here is a demo we have on our webpage. So this is actually a Beautif in the browser, and as you hover over it, you see at the bottom the timestamp from where this specific pixel came from. I will talk more about Beautif.js a little bit later on. But this is a really nice feature in case you want to trace where your observation value came from. Now to our processing chain, we of course work on a global grid, so we don't use for processing the MGRS grid for Sentinel, but a global projection. In our case, lat long, so WHS 84, where zoom level 13, so we are assuming the WMTS system of tile pyramids and grids, and zoom 13 matches best the Sentinel-2 resolution. So we're at the equator, we're around 9 point something meters, which matches the 10 meters resolution of Sentinel-2. We do parallelization in various levels. So first we split up the world into zones and parallelize this over some nodes on a celery cluster. Then within the zones we do a CPU parallelization over the process tiles, which are basically WMTS tiles but a bit larger. So we use meta tiling for that. This also has the advantage that within zones we can actually cache at least some of the Sentinel-2 images, because as you might be familiar with, it's using the JPEG 2000 compression, which works well in terms of compression, but if you read chunks of the image from an object storage, it's quite inefficient. So if you know that you need the whole scene anyway, we found out it's much better to have it on disk. Actually, we are converting it there to a tiled Beautif and then read it from there. Yeah, we do it dynamically, so our software figures out the overlap of the Sentinel-2 scene with the process zone and then decides whether to cache it or not, which has the advantage that we can read in parallel from the object storage and from the disk, so we don't overload the disk and we don't overload the object storage. So there's a sweet spot in between where the I/O is optimal in both cases. Yeah, we read the data as temporary cubes, so they are already gridded into our target grid. And yeah, then we reduce it to a layer and write it as a tiled output. I will come back to this later. So here you see our gridding system. So the green lines show the process zones. They are big enough that whole Sentinel tiles fit into it, but not too big so that the processing zone will take too long. So it's a compromise there. We found works out pretty well. And this actually matches the zoom level 6 WMTS tiling scheme. The software, the main package we are using to process our data is called Machete. It's an open source Python framework. It works in that way that you can define your Python process. So it's basically a Python file with an execute function, or it can be a Python module with an execute function. And then Machete would take this and take the data, split it up into tiles or in chunks, and apply this function to it, and then writes it as an output. So we have various input types. So for raster input, we use rasterio. So we can read everything that rasterio can read, or everything that GDAL can read, because rasterio is using GDAL. And for vector, the same. So we're using Fiona, and we can read everything that Fiona can read. Oops. What happened here? Yeah, sorry. Yeah, so it gets read. Then within this execute function, you can get every raster input gets converted into a NumPy array. Every vector dataset gets converted into a GeoJSON dictionary. And so within your process, you can make use of NumPy, SciPy, Pillow, scikit image, Shapely, So whatever Python package you're familiar with to process your geodata. And as an output, so we can write, of course, into single geotiffs or in tile directory geotiffs. It's basically, we are using, again, the WMTS scheme, but instead of writing PNGs or JPEGs, we write geotiffs. And it works out pretty well because this is a type of data format which can be written in parallel. So you can have your, 100 nodes and write into the same dataset, which is simply split up into multiple files. We also have a plugin system. So you can write your own Python extensions to Mapcheta. So for example, we have an in-house and satellite archive reader, which uses the data from AWS or Mundi. And if you read it, then you get an X-array back where you can do your processing. And you can also output it as an X-array if you want to. So for EOxCloudless, it looks like this way. We are using our satellite archive plugin. So it works for Sentinel-1 and Sentinel-2 data on both Mundi and AWS. Then as a process, we have our own Cython package, because Cython is a little bit more, a little bit faster than a pure Python implementation to do the mosaicing. And then the output is geotiffs on a tile directory on S3. Yeah, the tile directory, as I told you, it's basically the same as WMTS with a little bit more features to it. And the basic directory structure looks like this. So at the root, you have a JSON file, which describes the pyramid projection and the tiling scheme, so that our software can figure out how to map file paths to geolocations and the other way around. So this way, you don't have to build an index file or an VRT, which can get fairly large, because building a VRT out of millions of TIFFs is not efficient, especially if the file paths are predictable. I talked a couple of days ago because I found out that Esri is using a similar system. So yeah, we might get together and fleshing this out. So you can look at it like as an cloud optimized geotiff, but it's simply split up into multiple files. So you have a tiled structure and overviews to it. And it's suitable for really large data sets. So if we're talking about a Zoom level 13 mosaic of the world, so it's a 10 meter coverage worldwide, you need to split it up into multiple files at some point. We are also developing a tool called Geotiff.js. It's a JavaScript library written by a colleague of mine. It can parse geotiffs in the browser. So what you can get, so you can take a geotiff lying on an object storage, for example. It loads into the browser, and then you have access to the real data of the geotiff. So you don't have to do any reductions as you would have to do with PNG or JPEG. But you can really access, so in terms of Sentinel-2, for example, the full 16-bit integer values. And last year, we had a master student who combined the Geotiff.js library with OpenLayers. So he wrote a plugin so that we can access with OpenLayers a Geotiff tile directory and display it directly in the browser. So for example, use an elevation model and do some calculations there, or do some color corrections on our raw mosaics. Yeah. Currently, we have a work in progress to do, Fabian and me. So the initial idea was to finish it at Phosphor-G, but maybe we will not make it until then. We want to enable Geotiff.js to use a tile directory as input instead of a single tiff. But we have to tackle some hard questions, so how to define the tile matrices in a very explicit way. The way I did it now was just so that my Python package that does the tile pyramiding stuff can know which pyramid scheme it has. But we have to flesh it out a little bit more so that other clients can better use it. Then there's another idea. I mean, for us, it's a processing output, but for the next person, the mosaicing or whatever we produce is a processing input. So we are thinking about how we could apply stack on the tile directories. And we have an issue here because it's potentially millions of files with predictable paths. And if we use one stack asset per file, it may be not that efficient to crawl everything. So we're thinking about maybe using or creating a stack extension for this that uses, for example, an URL template. So the same way that WMTS uses endpoints. What we also found out is that we needed to aggregate, of course, the Sentinel products, because when the Sentinel satellites flies and then gets data, it actually does it via data take. And on the ground station, the data take is being split up into the granules, which overlap. And if you have this on an archive and you make a query to a catalog, what you get is you get multiple granules coming from the same data take. So we found out in our 2016 campaign that we get some weird artifact somewhere, and found out we didn't take into account that the actual data overlaps. So what we now did is so our Python package would abstract this away from you. So you don't access the granules, but you access basically the data takes in order to minimize duplication in data reading. And interestingly enough, there's a difference between Mundi, the DS, and AWS, because AWS stores the data strips, the data strip IDs, and Mundi stores the data takes. So the difference being that a data take is split up into data strips at that point where a different ground station receives the data from the data take. So I just wanted to put this into the room that if we talk about ARD, at some point we might to abstract so these kind of internal tiling schemes of satellite products to the user. And yeah, as mentioned many times, we still have to do a BRDF because we got stripes in our last run. And this is also something to consider. So if we abstract away from the user the whole granule and the internal tiling scheme and do the atmospheric correction, we might think of doing this as well, or putting this into a certain level of ARD standard. So to put this into a summary, you can read these points as an hierarchy, I would say. I think that the most basic and most important metadata we need to have for satellite imagery is proper masks. So if I do some processing, I want to know beforehand whether it really pays off to read the data, instead of I'm finding out later after I waited that it's full of clouds and where the clouds are. And with Sentinel-2, we have some special cases. So the original cloud masks, they show in the Atacama Desert, the most driest point on Earth, or area on Earth. It's full of clouds, so we got a lot of no data patches there until we found out it's all masked as cirrus clouds. The same issues we have in Tibet, so I guess it must be somehow correlated with sea level height as well. So yeah, it's just food for thought. What's also important is atmospheric correction, BRDF correction, and as further you went down, the more specific you get to the requirements of the user. So I guess the first points are important for many of us, and then for some user it might be important to have a data take view instead of a product view. And the endpoint or the most high level ARD product would be delivering a satellite coverage already in the analytics grid of the user, because most of the users would then be ML companies, for example, who don't want to care about reprojection and stuff as well. So that was our two cents. Thanks for your patience.
Thank you. That was really cool. We don't have a ton of time, but if there's any questions, anybody have a question? I've got several questions.
Yeah, I have one question on the Mosaic. Did you Mosaic also Antarctica data from Sentinel-2?
Yeah, the few data we have. But yeah, the gridding system we use is not optimal for Antarctica.
Okay.
But yeah, we simply tried it out and got some.
Okay.
You can actually see it on S2 maps.
All right.
What we got. Yeah.
Thank you.
Okay, I have a quick question. I've got a bunch, but we can talk about it later.
Yeah.
So can I, like, do you have mosaics of all these different bands and even Sentinel-1? Are they separated? Could I combine these and create my own false color mosaics and choose which bands I want to use? How would I do that?
Yeah, sure. By using Mapchete, for example, so
Okay.
you can use this tool and the endpoint of the
And say
S3
what
storage.
bands I want. Okay.
Yeah, and read it and then say which bands you want to have and combine
Okay.
it in a different way.
Okay.
That's our workflow. I mean, we store 4 band geotiffs, including the near-infrared bands, and then we create an RGB version of that. And so this is a chain of.
All right. Other question.
Yeah.
Pixel provenance. Like, how do you have a raster showing which pixel comes from which source image? Because it looked like you tracked that information.
Not for the last run, because we're using an algorithm that averages at some point multiple pixel values.
Okay.
But we do some outputs that have it. Yeah,
All right. Thank you again.
welcome. Thank you.
Hey, everyone.
All right. Next up, we have Sean Harkins from Development Seed.
Thanks. How's everybody doing? Sorry, I didn't want to put that too high. I apologize preemptively if I cough and blow everybody's eardrums out. I'll try and turn my head, but this is really close. So I'm Sean from Development Seed. I'm an engineer. I'm focused mostly on making Earth observation data easier to use and locate for scientists and general users who need to get the best observations possible. Most of my work's focused on building large-scale data processing pipelines for our partners at NASA. But I also work leading out some of our efforts for doing STAC search APIs and some of the front ends for surfacing that information for building search and EO data utilities. Oh, sorry, let me go back one. So one thing to note, I put my colleague Vincent Sarago's name first on this list because while I did some of the early conceptual work for this, and my colleague Drew and I were kind of involved in support and advisory capability along the road, Vincent really did most of the technical implementation of this work. He's really the best evangelist we have and the best resource that we have for working with COGs and Rasterio and recognizing how putting them together can build really great and functional applications. So if there's any questions that I can't reach on a technical level, please get in contact with him. He's so enthusiastic to talk about this stuff all the time. So since we're at an ARD conference, I think this slide has been pretty ubiquitous. Everybody has talked about what is ARD, and again, the fact that there's not a well-defined set of criteria that we use for ARD, and everybody has a different opinion about it. Just in the context of this presentation, I'm going to talk about 2 points, image clipping and image compositing. And this list is actually from a blog post that Chris Holmes from Planet put together, and I think it gives a good kind of concise set of points that we can use to represent or define what ARD is. For the rest of this presentation too, you just kind of have to, with your imagination, think that we're already working with level 2 data. So somebody has already produced some data that has proper usable data masks, atmospheric correction's been done, we're assuming great pixel alignment and sensor alignment, and we're just gonna worry about the image clipping and image compositing portion of this. So what are some of the problems that we're trying to solve with this work? We have a few ideas that we want to address, and because we work in a lot of different areas, we see the same kind of problem sets all the time. And we wanted a little bit more of a generalized solution that we could use to deal with these. The first one is flexibility. So Joachim just gave a great presentation and showed some amazing work that they're doing for generating global scale mosaics. But one issue that we see when we were doing the exact same or very similar work before is that these global scale mosaics lack flexibility. So we're not able to define very dynamically the images that we can use in the stack, how we want to prioritize those images, which pixels that we want on top, which pixels are more valuable to us. And at that level, we're not able to prioritize within a single image or a stack of images which pixels are more important to us. So these are some of the things that we want to think about when we're generating mosaics. We want to be able to give consumers absolute control of the stack of images that they're using, and within those images, which pixels they're selecting as well. Another big issue that we run into is cost. A lot of our clients, again, with this flexibility, you're talking about like a really exponential number of combinations that people can select in order for choosing a stack of images and prioritizing those images. If we were to generate and pre-render mosaics for all the possible combinations that our clients might want to view, our storage costs would just be outrageous. So we have to think a little bit more strategically about how we can solve for that problem. And I think that's also, several people in several presentations have mentioned this concept of on-demand data. And I think that stems from just our human feeling that we don't want to pay for something that we're not going to use. Pre-generating something, having it there as a reserve is great, and it's always going to lead to better performance. But often the concept of saying, I'm going to pay for this and never use it is really problematic, especially for managers. So we want to try and reduce those costs and make things as on-demand as possible. Another reason that we want to use this dynamic tiling and web Mercator tiles is everything that we use eats tiles. So all of our machine learning pipelines, relatively, I guess, almost all of the open source machine learning and object identification libraries that are available now, they have some kind of tile ingestion pipeline. And a lot of them actually include utilities for clipping and chopping larger images into tiles that they can use for ingestion. So it's a kind of standard format that we can use to feed machine learning pipelines. It's something that we can use to consistently scale and shape data that we can feed to these pipelines. So it's just another way to think about how do we get data in and out of our models. So all of this too builds on work that's already been done in the open source community. So we really are kind of standing on the shoulders of giants with most of this work. I don't know if any of you know Seth Fitzsimmons. He was the first one to pioneer this concept of dynamic tiling using GDAL, so that we could read a COG dynamically and render a tile as a byte stream directly to the client. And the project that he started was called Marble Cutter. Of course, none of this is possible without GDAL and Rasterio. So almost all the work that we do is completely built on the top of these libraries, and we owe great thanks to the open source community who's put them together. And there's also some great parallel projects happening now as well. Dion Hafner has built a dynamic tiling library called Terracotta, and we're actually trying to incorporate some of the great ideas he has around boundary edge effects back into the dynamic mosaicing that we're doing. So a lot of the work that we're doing now actually kind of grew out of some consulting work that I did with Seth Fitzsimmons for the open aerial map. We were running into a lot of situations, especially in disaster response scenarios, where we were building machine learning pipelines for detecting damage results and trying to do damage results dynamically. But one thing that we really had a problem with was we needed to kind of define these mosaics on the fly. So Open Aerial Map has a huge set of drone imagery, a huge set of imagery that gets donated by Maxar. We are able to query specific images out of that set, but we don't have a good way of querying for a subset of images and then using that query as an input for a mosaic. So we built, using Marble Cutter, we built a way to basically map a query into the tiler so that we could dynamically tile images based on a date range, based on a location, based on some criteria. But the big problem that we had with that was for every tile request, because these tile requests are completely stateless and there's everything is happening on the fly, every new tile request required a new metadata request. So you can imagine when a machine learning pipeline is looking at multiple zoom levels, or when a regular user is looking through the browser application, that becomes extremely chatty. We were generating thousands and thousands of requests against our API constantly and completely unnecessarily. Another big problem was that our tiling code and our candidate search code were really coupled. So we couldn't generalize this to use with other metadata providers. We were tied to the metadata model that we were using, and we also had to make our code so that it was really tightly coupled to that. And it also didn't really allow user input for prioritizing images. So users could not go in and say, I want to change the criteria of my search so that I can put these images on top or these pixels on top. They were limited to the kind of pre-generated search results that we returned. So with some of that in mind, Vincent and I set out a few goals for this dynamic mosaicing work that we wanted to do. And the first one was to give power users complete flexibility and total control of selecting the best observations that they could for their use case. The second was that we wanted to not build a monolithic solution. We really wanted to let people, I don't know if people are familiar with DevC, but we kind of have a strong philosophy of open sourcing a lot of our work. And Vincent as well is a big proponent for open sourcing all the work that he does. So rather than build a big solution that everybody had to use, we want to build smaller components that people can incorporate into their own solutions. And most importantly, we wanted to decouple candidate search from the mosaic and tiling to avoid this chattiness problem with our API. We wanted some way we could abstract away the concept of the mosaic and separate that from the concept of searching for candidate images. And most importantly, we want to make it fast. None of this works if there's high latency. None of it works if it's slow. We have machine learning pipelines that we want to completely leverage GPU usage, and we want to make sure that our utilization rates are high. So if tiles are slow, it's not going to work for us. Besides some of the other stuff that I talked about as far as prior art, all of this, again, is built on top of cloud-optimized Beautif technology, and we're also leveraging STAC metadata for the candidate search that we're doing. So I'll talk a little bit more about it later on, but while STAC is not necessary for generating and building dynamic mosaics, it really helps us. It has the concept of being able to prioritize images and order images based on certain criteria in your search, and it really gives us a lot of flexibility when we're trying to find a uniform standard for returning records. So how does this work at a high level? This is actually really similar to some of the work that we just saw for how we generate static mosaics. First, we want to select some candidate images based on criteria in an AOI. Then secondly, we want either via the API or by some user ordering criteria, we want to be able to determine how we're going to put these images in order in the stack. And then we have to figure out for each tile that we're generating for their Web Mercator tile request, which images intersect that tile. And then even at the next level, we have kind of a two-level prioritization. We're talking about prioritizing images within the stack, and then within that stack, we can also kind of go one beyond that prioritization and prioritize which pixels we want to select from that stack. And then finally, using the pixels that we prioritize, we want to fill our candidate image, or we want to use pixels from our candidate images based on the priorities we define. So the thing that we built in order to separate search from the actual mosaicing process is this new specification called Mosaic JSON. And this is just our way to abstract away the concept of a mosaic and make sure that we don't have to tightly couple our tiling code to any one search or query API. So what it does is allows a single metadata search, which can then be reused by multiple tile requests. So we're taking care of that chattiness problem that we have with our API. We're using quad keys to link the candidate images to our tiles spatially, so we can have really fast spatial search without necessarily having to use a spatial search library. We can just rely on the structure of the quad key in order to infer where our location is. It allows within the Mosaic JSON ordering and prioritization of your candidate images, and these again are durable and shareable and cacheable. So just think of it as a durable endpoint that a Mosaic tiler can use to understand how it's going to fetch images in order to draw. So let's take a look at how this works in a little bit more detail. We can see over on the left side here, this is the result of our stack search. So let's say that I made a search for all the images within a certain AOI that have a certain level of cloud cover and whatever band combination that I want. Within that search result, I'm also asking the STAC API to order my results in descending date order or ascending date order. Sorry, descending. And so I've gotten this list of stack results back that I can then use to transform into a Mosaic JSON. So internally, some of the tools that we built actually have these transformation libraries, but again, it's a really simple process to decide which Web Mercator tiles my candidate images are going to intersect. And then within, you can see the quad keys on the right side and the ordering of the images within each of those quad keys. This is a really simplified example. So the current Mosaic JSON specification allows just direct paths to imagery. But again, if your image is composed of multiple assets, we can also include those within the Mosaic JSON file using well-known band keys so that you can just pull out the asset that you need. The structure that happens within the quad key is really flexible. Another thing that I didn't really talk about in too much detail, and I think gets overlooked with stack records as well, the most powerful thing is this ability to kind of have a uniform and combined search output. Most people, when they're searching for imagery, and especially when we're working with machine learning models, we want to search for imagery iteratively. We don't necessarily have one kind of overarching search that's going to capture all the records that we want to use. We want to be able to say, okay, let me search for a certain date range, get some data back. Oh, I need to look for some more. I'll do a second search and get those. But because of the flexibility of Stack, we can combine all those into a single set of combined Stack records, which we can then translate into Mosaic JSON. The next kind of Lego block that we're using within this pipeline is RioTiler Mosaic. It's a RioTiler plugin that allows for tile creation from multiple observations. So rather than just rendering a tile from a single image, we can use an array of images and a stack of images in order to render out a tile. It supports multiple pixel selection methods, and we use some strategic multi-threading to optimize our data retrieval for pixel selection approaches. So again, what's happening here is once we've defined our set of candidate images, we can also use the default pixel selection method as first. So that's basically just going to go through the individual candidate images, pick the first pixel, and fill the tile using the first available pixel. But if we want to override that ordering methodology, we can support a bunch of other pixel selection methods, and we can also inject our own custom pixel selection methods if you have a way that you want to specify what pixels should be prioritized within the tile. So putting all this together, we've defined our Mosaic JSON. We talked a little bit about the plugin that we're using for RioTiler in order to generate Mosaic tiles. But we've also put all this together in kind of a sample project. So internally, we use all these Lego blocks in kind of a different context. But just to get people started, Vincent's put together this CogGeo Mosaic project as well. It's a serverless framework with a Lambda for generating tiles defined by a Mosaic JSON. It also has some nice functionality for allowing users to dynamically select bands using well-known keys. And you can pass it any kind of real color formula or color map that you want in order to change the rendering output. And so at a high level, what happens is a user, whether it's a machine learning pipeline or a user in a browser, is going to make a tile request to the Lambda using this Mosaic JSON key. We go out and check the candidate images for that Mosaic JSON. We select the pixels that we want, and the Lambda is going to return a byte stream with the tiles and the selected pixels back to the browser. Let me see if I can just show. Again, I was not as brave as the presenter from Esri who did a live demonstration, so I'm gonna put a quick film of this on. So this is just a quick demonstration of some early implementation of this work that we did with a partner from USGS. And you can see here, as I zoomed in, we're initially making a request for a Mosaic JSON. And that Mosaic JSON definition is being used to go out and fetch pixels from COGs to generate these tiles. So we can see there's a bunch of cloud on the upper right side. And so now I'm making a completely new stack request and generating a new Mosaic JSON file that reduced that cloud reduction. But we can see we don't have enough sufficient data to fill all the tiles. So I can go back, check back in time a little bit, and see if there's any other available data that I can use to fill those tiles. And using this date range, there's sufficient pixels to fill everything. And again, this is actually an early implementation of this, so the latency that you're seeing is actually quite slow. We've improved the speed and performance of this quite a bit. And like I mentioned before, too, we have flexibility in how we can define the band combinations and rendering that we use when we're pulling tiles. So here we can specify an agricultural band combination. And again, these are all done after the fact. So using the same Mosaic JSON, we can kind of specify any band combinations or color maps on top of that we want to. And beyond just band combinations as well, we can also specify more complex band formulas. So over on the right side, I'll show in a moment how we can generate an NDVI from this as well. Actually, let me just go to the next slide quickly. And one thing that's kind of an interesting artifact or something that we noticed when we were initially doing this work, it's great for Landsat 7. Because of the SLC failure, you traditionally would see striping within all of your Landsat 7 data returns. But because we're doing this on-the-fly compositing and we're selecting pixels from multiple images across the time series, we're able to do this gap filling dynamically within our tiles. And again, it's not a perfect solution for everything. Obviously, there's cases where pre-rendering tiles is going to be more cost-effective. You can see that over the life cycle of a project, things are going to be more cost-effective the more times you request a tile. So again, in some of our machine learning models and some of our inference training, this doesn't necessarily become cost-effective if we have to do multiple inference runs. And just quickly, I'll talk about some next steps. I'm working separately on building a direct Mosaic JSON endpoint from our stack-compliant SAT API. So rather than have the client or whatever intermediary be responsible for generating their own Mosaic JSON, we'll be able to make a query and get a Mosaic JSON back directly from that. That has some implications for how we pass things around and sizing. We're hoping to extend the Mosaic JSON spec with assets so that you can kind of generalize band combinations rather than using well-known band keys. We're working on optimizing cache strategies for hashing Mosaic JSON. So if you use a Mosaic JSON and you try and generate the same one, that hash should be the same, and we should be able to use the browser cache for tiling. And we actually have already accomplished this bottom one, so extending the Mosaic JSON to facilitate pixel provenance. Inside of the Mosaic JSON now, we're including the actual stack ID for individual records so that any user can go back and click on a pixel in a tile and determine what the original cog that was used for generating that pixel was. Thanks very much. And Vincent wanted me to ask everybody to send PRs as well. We're always looking for more contributions, so please have a look at the repositories and try and help us out. And if you want to get some more information on that, he has a great blog post on our blog called Cog Talk, Part 2, Mosaics, which kind of describes in a little more depth some of the stuff I talked about. Thanks very much.
Thank you. Really awesome stuff. We don't have a ton of time. Maybe one question, maybe two, if you make it quick. Anybody? All right. Well. Oh, okay. Keep going.
Thank you. Is there any specific part of your current developments where you're looking into collaboration? Like, is there any priority?
No, actually, the best way to look is go on the Rio Tyler issue log, and there's a lot of things that we're looking for. So I think we're looking for some assistance in, again, some of the contributions we're doing on how we can manage edge effects with tiles. So we're trying to incorporate some of the work from Terracotta directly into the tiler that we're using now, and there's a lot of space for contribution for that if that's something you'd be interested in.
Okay, thank you.
All right, thank you again. Next speaker.
Okay? It's okay? Yeah, perfect.
All right, next up we have Samuel Hunt.
Okay, we are in a bit of delay, but I promise I will be quite quick, because I just want to introduce a framework on how to assess commercial satellite mission quality, which is coming from the European Space Agency, and we, NPL, and Telespazio, and other companies are involved there. Yesterday, if you remember, I was talking about really in-depth into methodological concepts, providing really in-depth examples. So some of you asked me about how we can actually assess these issues into some sort of audit, some framework where we can categorize how in-depth the quality of the product is. So I'm going to go very quickly into the motivation and the background, some development of other QA frameworks and some examples, how it can be done for a commercial mission, and so on. So this is a very old story, because it's not happening in the EO sector, but for example, I'm coming from a National Metrology Institute, let's say like the NIST here, and for us in the 19th century, we've got the convention of the meter, where we actually, they actually convene into what a meter means. Then we developed the International System of Units, and we got something called the Mutual Recognition Agreement, where we actually have the radiometric standards there, which is the cryogenic radiometer, and we've got some optical measurement standards where we have a very, very tight protocol in order to have a comparison between different NMIs. It's something, it's very protocolary, but is the difference, let's say, between NMIs and EO sector, where there is no clear protocol, not clear specifications on how to compare. And actually, let's say this is not coming from the scientific, the original idea was not coming from the science, was actually coming from a commercial point of view, because it was really interested at that point to understand whether the parts they were building in one place were actually useful for another country. They were using different metrics and so on. So for example, you've got this example of planes which are built in different, let's say Airbus or Boeing, are building each part in a different country, and we actually need to be very clear and very sure that they can fit all together. So let's say traceability is an unbroken chain of different steps, where we, in the radiometric point, in the radiometric field, we start with a cryogenic radiometer, we move into a field radiometer, and so on, till we come to a tile, or a spectralon, or a black body, and so on. So one of the important areas we need is the comparison. This is in some ways done in the EO sector. We have seen here comparisons between different products, let's say Landsat to Sentinel-2, Planet to Sentinel-2, RadCalNet, other sort of surface flux nets, and so on. So this is, in a way, not very standardized, it's done. So then you've got documented procedures. This is also in some sort of way done. So you've got from papers to reports and so on. Then we've got rigorous uncertainty analysis, which, let's say, is not so done. So usually when we compare the things, we just compare one satellite with another, but we don't understand whether they fall between actual uncertainty. Something we do in the comparison of radiometric standards is actually we've got a metric where we do not only account for the difference between the two values, but we actually account for the uncertainty in each one of the values to understand whether they agree or not. So actually the criteria of agreement takes into account the uncertainty itself. And this is something that is not done in the EO sector. And finally, the audit, which can be a bit tricky, especially for commercial missions, but this is something important where an external body actually comes and makes sure that the product and so on is correct. So I'm just showing you an example of how we understand the traceability chain very quickly. So on the top, you've got the cryogenic radiometer, which is the standard of the optical power, where we can get to the 0.005% of uncertainty. We move into a trap detector, which converts this into an irradiance level, then comes into filter radiometer, black body, where we can actually convert it into a radiance standard, and finally an FEL, which can come into a diffuser, which can be the irradiance or radiance standard for a diffuser, or so on. So till in the end, you bring all these steps down to an actual final radiometer, which in this case, let's say, is a lunar photometer we have installed in the Teide mountain. Just to give you an example of this, because at each one of these steps, we document, we traceably document the uncertainty that is coming from each one of the steps, and it's a whole chain in the sense that you need to account for each one of the steps back to the cryogenic radiometer. But the problem is that in space, this traceability chain is typically broken, and we need something in. This was my colleague who put this. So basically, you've got some pre-flight tests and so on, and you can come with a PSF. You can put a point spread, a point illumination. Then you can make linearity tests. But many times, actually, what we measure pre-flight in terms of geolocations or in terms of radiometry and so on is completely changes in space, and we agree that we need some tests in space, some references in space, and many times it's challenging. So this actually emanates from the QA4EO principle, which is like critical data must and products must bring an indicator of the quality, if possible traceable to SI. By traceable to SI, I mean to the radiant power and so on. So back to the units of ampere and so on. That actually lets the user to identify whether the data they are obtaining is fitness for purpose. So if you want, for example, to detect a solar farm, you do not need a quality of a 1% uncertainty of your level 2 product. But if you want to understand, for example, let's say the carbon stocks of a country, possibly you are really asking for a level 2 product which has a lower than a 1%, which actually gets you into some sort of LAI estimates and so on. So we have performed an early data assessment on various existing new and future EO missions. So we have separated into different domains, from very high resolutions to high resolution, medium resolution, and low optical resolution. Then another area completely different is SAR, and another one is atmospheric missions. At each one of them, we have defined some preliminary requirements. So the idea is to organize different workshops that focus on data quality of different EO mission sensors. So, for example, here I think our colleague Enrico talked about it, but you've got a very high resolution RODA workshop in Frascati in November, where we are actually going to discuss the different possibilities of this EDAP framework. So just to give you a very simple idea, this is not coming out of the blue. So this is like building on different initiatives from 10 years ago, where we are starting with LTDP, long-term data preservation. Then we have the QA4EO framework coming from CEOs. Then we've got some initiatives like QA4ECV, where they were studying the quality assessment of essential climate variables. Then we got C3S, where it's also studying climate products at the quality level. And finally, we've got EDAP. So the principles. We are looking for high-level activities common to all EO missions. We are looking for an ideal case, although we know that an ideal case is not possible, but wherever possible is an aspiration. of bringing this ideal case. And actually, we want to grade the mission fitness for purpose for each one of the application areas. As I said, the assessment of the ideal case is not possible, and we know that in some aspects and some specific issues might not be falling into the EDAP framework. So the core of the development of the framework is this quality assessment matrix, where we have actually identified 5 different areas, from product information, product generation, ancillary information, uncertainty characterization, and validation. At each one of them, you've got different fields: product details, then you've got sensor calibration, product flags, and so on and so on and so on. So the idea is that at the very, very high level, we've got this quality assessment matrix where we can provide something very simple, like a grading criteria, where you go from not assess, not accessible, basic, up to excellent, or simply that is not available, this information, for the public. And for example, I quickly gonna give you an example of, for example, how we grade preliminary this one of the different items we've got there. In this case, the sensor calibration pre-flight. So you can see that it goes from not accessible, not assessed, not accessible, some basic, which would be, we have some values of comparison of our sensor to Landsat 8. So then you've got some intermediate, where you can bring some comparison at different scenarios. Then you've got a good case, where you've got different areas of calibration and characterization, and an excellent, which would be covering all the potential areas, for example, nonlinearity, stray light, and so on, and actually giving some uncertainty estimates, like, for example, taking into account the calibration using a diffuser, where you take into account the non-uniformity of the diffuser for each one of the pixels, taking into account different areas, different viewing informations of every pixel in the diffuser, and so on. So going into very, very detail. So I want to be quicker because I'm already... another example would be uncertainty characterization, which is quite... for most of the missions, it would be basic, I would say, or not accessible. But for example, if you provide some basic, in the case of basic, what could be? Like, for example, a mission providing a reference of, let's say, our uncertainty is 5%, better than 5%. So that would be a basic assessment. If you want an intermediate, for example, you are providing values of uncertainty at level 1 or level 2 based on, as I was mentioning yesterday, for example, some noise model combined with some gain uncertainty. Then if you want to do it good, then you are bringing the effects, the uncertainty due to stray light, the uncertainty, for example, at level 2, the uncertainty on your aerosols, and so on, and so on, and so on. That would be, for example, the case of the Sentinel-2 estimates. Then if you want excellent, is something that people, as far as I know, has not done operationally, which is, for example, apart from uncertainty values, you are also providing the covariance information in the spectral, temporal, and spatial domain. So that would be a really maximum level. So the reporting assessment is actually to generate a template report for EDAP quality assessment that simplifies the comparison, and we don't want to be very prescriptive, but the idea is to have this on the top level, this quality assessment matrix for the people who just want to quickly understand how the product is fitness for purpose. And then obviously, once you want to go into depth, you've got a report describing each one of the criteria, each one of the very, very into detail of why, for example, this is blue, why, for example, this is green, and based on which criteria you have applied. This is an example ongoing. It's not yet finished, so most of them have not been assessed. But for example, you can see here that product format is good. I went into a look. I didn't. This is OceanSat, which is an Indian mission, hyperspectral Indian mission for ocean color. I went into. You have the metrics on the top, and I went into the details of the report. a bit. And for example, for product format, you can see that what in the report, what they describe is that they went into several dozens of products throughout all the archive, and they have checked that actually the product format is consistent. So they are following some standards and so on. So it's a whole study about it. And they also describe other things like the sensor calibration and characterization, product flags, which are basic. For example, ancillary data is not accessible. That means they don't have any ancillary data available. And some conclusions here. There is a need, as I said, to provide that the EO missions provide independent quality assessment of satellite missions, so they can understand the fitness for purpose. That is kind of an audit, as I was mentioning before. It can be quite tricky for commercial missions, I understand, but it's something needed that somebody else checks actually the fitness for purpose of the data. The ARD producers can benefit from this standardized quality assessment to ensure that their data products are traceable and they are trustworthy for them. And basically, the EDA mission is trying to provide this rigorous approach based on the quality, on the QFREO principle. And that's all. Thank you.